Good afternoon, everyone. Good morning to all of you on the West Coast. Welcome to our next webinar in the Public Safety Innovation Series. Thank you for joining us today. I'm Ari Vidali. I'm CEO and founder of Envisage Technologies, and I'll be your host for today. Just a couple of housekeeping notes before I introduce our speaker. First, our topic today will run at most 1 hour with approximately 45 minutes of presentation and about 15 minutes for our speaker to take your questions. Please feel free to enter your questions at any time into the chat box in the lower left corner of your screen. Also, we are recording the webinar today, so you will be able to share it with others after. We will be following up after the meeting with details about the video. Okay, a little bit about us before we get started. Envisage Technologies is the leader in training and compliance technology for public safety professionals. In short, we ensure that our first responders are trained, equipped, and ready. With over 1.1 million first responders using our technology, we started this webinar series because we were frustrated that great ideas and best practices, those that can save lives, are not getting out there and being adopted fast enough. We're really passionate about solving that for public safety and raising the bar on training. We believe fundamentally that readiness saves lives and are committed to improving public safety through awareness and innovation. Today's webinar is really no exception. A core responsibility of the leaders in the fire service is not only to understand the health hazards our firefighters face, but to aggressively mitigate them as efficiently and completely as possible. To understand these hazards, we must engage in in-depth research that can inform our actions on the Fireground and on the training ground. Our speaker today is dedicated to understanding fire dynamics and firefighter health and safety risks. We are fortunate to have with us today Dr. Gavin Horn, Director of the IFSI Research Program at the Illinois Fire Service Institute. The Illinois Fire Service Institute has led a series of trailblazing projects with UL's Firefighter Safety Research Institute and the National Institute for Occupational Safety and Health to study the cardiovascular and chemical exposure risks on today's fireground and training ground. Gavin's research interests include first responder technology development, firefighter health and safety research, material testing and design, infrared imaging, and non-destructive evaluation. He has a PhD in mechanical engineering and also serves as a volunteer firefighter and engineer with the Savoy, Illinois Fire Department. Dr. Horn, thank you for being with us.
All right, Ari, thank you very much. I really appreciate the opportunity to be part of your Public Innovation Safety Series. And thank you, all those who've joined us online for this webinar. The information that we're going to cover today is part of a very large study, and we'll try to put it in the context of the overall study. But after the introductory material, we're going to go into a fair bit of detail on some of the data and the information and what that means. This is all currently being reviewed academically to make sure that the science is right, and that's a critical aspect of the research that we do at IFSI. But this is also an opportunity for us to have the fire service peer review the work that we're doing so that you can have the initial look at some of this data and our initial translation of it, and we want your feedback. So please ask questions in the chat box as we're going through this. We'll try to answer them at the end, or we could follow up with us afterwards so that we can make sure that when we put the final toolkit out towards the end of 2017, that we've had the input of the fire service as well as the scientific community, so we can make sure that we have the most bang for the buck and everyone can gather the most information from this. And while again it's my pleasure to be able to present this information to you, I am representative of the larger team that we have. This is a massive collaborative effort that we have been able to bring together. And I want to first of all mention the project leads, Denise Smith, who is a research scientist at IFSI as well as a professor at Skidmore College, leads our cardiovascular research team. Kenny Fent from the National Institute for Occupational Safety and Health, or NIOSH, and his team of 10 to 12 individuals who came in have done some of the great work in the world understanding the chemical exposures that firefighters face. and Steve Kerber and his team from Untitled Labs Firefighter Safety Research Institute, again, brought down a huge amount of manpower and equipment in order to combine and to compare the work that we've done here in the field with some of the work that they have done for the last decade or so in a laboratory at Northbrook. Of course, the team would not be complete without our project partners at Globe, who were critical in helping us with the equipment for the study, as well as designing the study from the very beginning to the end and allowing us to get the information out to the right standards organizations as well as to the public fire service as a whole, in addition to outlets such as this. We have a technical panel of experts in the fire service as well as fire media from across the country. And again, they've been helping us to ensure that we're asking the right questions at the very beginning and helping us to translate and disseminate at the end, which is again where we hope that you will continue to join with this panel of experts as we translate this research and get it out. A project like this is just not possible without some significant funding, and we couldn't do this without funding from the Department of Homeland Security through the AFG Fire Prevention and Safety Grants. It's a massive undertaking, and we appreciate the funding from the federal government for this. There's also a component of this that was funded by NIOSH, particularly looking at some fire retardants, which we won't get into detail on right now, but funding is also acknowledged from them, as well as the requisite small talk there where we have to indicate that mention of any company name or product does not constitute endorsement by the federal government, particularly for NIOSH. Now that we've got all of that background done, what are we here to do? The goal of this study, of the overall project, is to better understand how the work that we do, the modern Fireground, the fires that we're responding to, are related to the leading health issues that firefighters face. We're particularly focused on the cardiovascular events and the chemical exposures that can eventually turn to cancer in those who might be at risk. We're trying to focus on both of these in one individual research project. And in doing so, we're going to look at it from a couple different avenues. We look at firefighting in the most complete manner that we possibly have, looking at the different types of firefighting events. Not all firefighters do the same thing, so we can look at things from inside operations to outside operations and overhaul and different levels of risk and exposures they have, both thermal and chemical exposures. We can study a little bit about tactics, from interior firefighting operations to a transitional attack, how those might affect the risk, and again, what are some of the things we can do on that back end to reduce those risks or counteract some of the negative impacts we have. For example, hygiene. What's the impact of cleaning skin and gross on-scene decon at reducing each of these risks? So there's multiple components to the study, and we're trying to break it down into small, understandable chunks that we focus on for peer review, both, again, scientifically and in the fire service. For this presentation, we're going to focus mostly on the thermal side, and that is really going to focus on the fire dynamics and the heat stress on the firefighters. And in the near future, we'll start to disseminate more information in the cardiovascular strain as well as some of the chemical exposure aspects of this study. So a little bit more background on fire dynamics. The work that's been done by our friends at UL as well as NIST to understand the development and propagation of fires has really helped us to get a much better appreciation for the dangers that are involved in today's residential fires and what are the hazards associated with firefighting, and a result of the rigorous study that has been conducted at those locations. They've been able to put some tactical guidance out there that can allow firefighters to put some numbers to the understanding about how different choices might affect the fireground, specifically how it might affect the environment as well as the structural stability. Now, one important aspect of those studies, they've been done in a very controlled manner, and that's necessary in order to have repeatable results, to have confidence in the data. But it's involved theoretically perfect firefighting. Every time that water was suppressed or ventilation was done with Steve or Robin or Keith or Mike controlling each of those in a very controlled manner. So it was turned off and on at specific times. And that's different than some of the variability that we have on the fireground. That was not included in some of those studies. It's also important to note that most of the focus is placed on some of the acute risks, particularly for the occupants of those structures. Changes in development of the fire, changes in structural stability, and how those would affect risk for flashover or structural collapse, both for occupants and for firefighters themselves, looking somewhat at the acute risk. Now, at the same time, at IFSI and at NIOSH, we've looked at some of the other health and safety risks. Realizing that cardiac events are the leading cause of duty-related deaths as reported by NFPA statistics, we also know they're far more likely to occur after the event, partially due to the significant cardiac strain that firefighting imparts. We also know that there's an increased risk for several types of cancer and that they can be linked back to the firefighting event. We're trying to understand how the exposure to some of the potentially carcinogenic compounds on the fireground might affect that risk. So there's been a great deal of research that has helped us to understand why we see each year about 45% of the line of duty deaths as reported by the NFPA journal as a result of sudden cardiac events. We also know, based on the work that's been done by our friends at Harvard, that firefighters immediately post-fire suppression are at 10 to 100 times increased risk of suffering sudden cardiac death compared to firefighters who are operating, doing station duties or non-strenuous activities such as those. We also need to make sure to remember, if we look at the injury statistics as well as the fatality statistics, for each fatal cardiac event, there are 20 to 25 non-fatal events that occur in the fire service. And we need to understand these are near misses and warnings that we need to take into account in addition to the fatal events. Now, there's been a great deal of work in this area, much of it done at the Illinois Fire Service Institute. You can see a couple of the reports on the left-hand part of this slide. You can download for free from our website. These are fire service reports that translate some of the peer-reviewed academic journals, academic research. But there's also been research done at places from Arizona through New York. What's important about all this information, while we've really started to understand more about the cardiovascular risk, we're limited in terms of the types of exposures to the firefighters. These are done typically in laboratories with very controlled types of firefighting activities, or in training scenarios with pallet and straw fires, not with the typical scenarios that we would experience on the fireground and that UL has been able to conduct in their laboratory. We don't understand yet how common household furnishings and tactics resulting in different heat exposures can affect the thermal responses in the cardiovascular system. And while we're not going to get into detail today on some of the occupational exposures, we know that the number of firefighters who have died from cancer or battling this disease is alarming, based on the statistics from the International Association of Firefighters Line of Duty Death Database or Firefighter Cancer Support Network statistics. There's also mounting epidemiological evidence from very large studies done across the country and around the world that is linking firefighting to certain types of cancers. What's important for us is how to characterize our workplace so that we can reduce those events, much like we're looking at reducing the cardiovascular events. At the same time, we've not been able to measure some of the workplace measurements that we need in as realistic scenario as we have done in this current study. So these may seem a little contradictory and difficult to put these three different areas together. So I hope these next couple slides will help bring it together, how with a single study we can link firefighting to reducing the risk for cancer and sudden cardiac events. So if we start off here with the exposures we have in the firefighter on the left, and we know based on the evidence from statistics and epidemiology that there's an increased risk for cancer and sudden cardiac events. In order to reduce that risk, we need to study what are those mechanisms that get us from point A to point B. And to do that, we start with the very basics of what are the firefighters exposed to. And we know fires produce heat and they produce smoke, which we're calling products of combustion right here. And what we need to do now is measure how we get from what the fires produce to what gets into the human body, and we're doing that on multiple different levels. We start off by looking at what's produced in the environment, the gases and the particulates from the fires, and the temperature and heat that are produced by those fires in the buildings. This is something that UL and NIST have done for a number of years in their studies. But the next level down from that is understanding what does the gear protect us from, and what stays on the gear in terms of particles or contaminants, but also the temperature. Because the gear is there and does an outstanding job of protecting us, but is not 100% protective, because we know that there's still some level of exposure to contaminants and products and some level of increase in core temperature and skin temperature in the environments in which we're working. Just because we have some exposures doesn't mean that we're immediately going to have cancer or sudden cardiac events. We have to understand how the body reacts to those, and that's what we talk about with the primary physiological responses. What are the things that the body is doing to respond to those thermal and chemical exposures. And once we understand those, and particularly individuals who might have to be susceptible for some of these exposures, that's how we can get the link to cancers and sudden cardiac events. Other components of this that we're interested in: how long does it take for the body to recover from these? What is that period where individuals might be vulnerable post-suppression for the cardiac events, as well as for further exposure to some of the fireground chemicals? What are the things that we can do to reduce, again, from a hygiene perspective of deconning the gear and cleaning the skin from a thermal exposure perspective? So this is the overarching view of the project. It's important to note that while we can measure each of these individually, for example, the temperature, the skin temperature and core temperature might not only affect thermal regulation and hyperthermia, which could have some cardiac implications. There's also some very important implications that could have to exposure for certain chemicals. So while we look at these individually, we're also very interested in how they come together when we do the cross comparison between the different aspects of the study. Again, we're going to focus on the bottom row here, the heat, from the environment to the gear to the skin and the core temperature, because that's the bedrock on which all of the rest of this work is going to be presented and hopefully to be understood. So the rest of that material will be coming out in the not too distant future. So the best way that we can actually describe this test is I'm going to sit back and show you a video that our friends at UL, Josh, has put together for us that describes the video, shows you some of the Fireground footage as well as some of the instrumentation in more detail. So we'll let this video play and come back to the live webinar here in about 3.5 minutes.
My name is Gavin Horn, Director of Research at the Illinois Fire Service Institute. For the last couple weeks, we've been working on a project that's many years in the making. It's one of the first times we're able to bring together the great research that's been done at the Illinois Fire Service Institute, working on the cardiovascular strain of firefighting, with our partners at the Underwriter Labs, working on firefighter health and safety, focusing on tactics and some of the changes in the modern built environment, and NIOSH, who has looked at the chemical exposures to firefighters on the fireground and various different types of firefighting activities. So we're really excited to have all of these different partners available, and the research that's been cutting edge in each of these different areas can come together for the first time here at this research project.
My name is Steve Kerber, the director of the UL Firefighter Safety Research Institute. We're here to create 12 consistent fires, measuring temperature, heat flux, pressure, victim tenability, so that our partners can measure the chemical exposure as well as the cardiovascular strain experienced by the firefighters during these experiments.
I'm Kenny Fent from the National Institute for Occupational Safety and Health, or NIOSH, and our part of this project is really to focus on what are the chemical exposures during firefighting. We're looking at what's getting into the air, what's getting onto the gear, what's getting onto the skin, and then also what's getting into the body. We're also looking at various ways to help control those exposures. Ultimately, what we're trying to do is figure out the best way to protect the firefighter.
I'm Denise Smith, a research scientist at the Fire Service Institute and also a professor at Skidmore College. And in order to look at the carcinogenic and cardiovascular risks that firefighters are facing, we've designed an experiment in which we asked 36 firefighters to actually come to the Fire Service Institute and do real firefighting in a modern fire environment in a building that we built specifically for this research. Before firefighters engage in the firefighting activities, we get complete physiological measures, including EKGs, blood pressure, breath samples, urine samples. It's a complete physiological workup. We then put them into the firefighting situation. They're assigned to specific roles based on exposure, and we measure all of those things again, the blood, the breath, and the urine, as well as the continuous monitoring of heart rate, EKG, and core temperature. And what this allows us to do is better understand the overall physiological strain, but also to understand how the tactics and what they're doing on the fire ground impacts physiology and exposure risk.
Okay, so that provides a little bit of background on the actual exposures that the firefighters faced, and a little bit of an overview of some of the data acquisition. So just for a little bit more information on the participants. Participants in this study were firefighters recruited from across the country, mostly from the Midwest, but we had some groups coming from as far away as Cobb County, Georgia, and Sioux Falls, South Dakota. We had to be specific about the firefighters who we recruited within a certain age range, non-tobacco users, because of some of the risks that the study included, as well as to reduce some of the potential confounders. It was important that each firefighter completed an NFPA 1582-based physical within the past calendar year of beginning the study. And those firefighters participated in some very specific roles, and we put these roles together in order to simulate a coordinated fireground operation. So in the first engine, 2 firefighters participated in the inside attack, which was a fire suppression scenario. They pulled a line and suppressed the fire. On the engine, there's also 2 firefighters who stayed outside of the structure, never actually went inside, and their job was to work on command and pump operators. So they did the actual events, but never stepped inside the structure. For the truck, 2 of the firefighters worked on the inside. They were considered our inside search team. They forced entry into the structure and then did a search and rescue where there were 2 victims within the structure. 2 other firefighters, again, never crossed a threshold, but they did the typical work that we might have on the outside of a structure. Horizontal ventilation, vertical ventilation, popping some additional doors, laddering the building, those sorts of things. Again, never on the inside of the structure. And then we also had a second engine who came in, and they were there for overhaul operations. Now, they came in and pulled the backup line or set up the rapid intervention team, but never crossed the threshold of the structure until the fire was suppressed and all the victims were removed. Once the inside attack and inside search teams came out, the overhaul crews masked up, went in, and completed overhaul of the 2 fire rooms. Pulled all the ceiling, pulled all the walls, cleaned everything up, did what we would typically do for a detailed overhaul operation. As I mentioned earlier, we also looked at different types of tactics. In each case, so if you look at the video here, we'll try to get this green arrow up. For a scenario like this, if we had fire in bedroom 5 and bedroom 6, all the scenarios had 2 compartments of fire. Our firefighters used 2 different types of tactics. Let me get rid of this thing here. So, interior attack, where the first line went through the front door and they moved in down the hallway and suppressed fires in bedroom 5 and in bedroom 6. The same firefighters also conducted firefighting operations using a transitional attack, where they pulled the full first line and then actually flowed water into bedroom 5 and bedroom 6 from the outside before transitioning to the inside and completing the suppression operations from the inside. The order in which the different groups did the interior versus transitional attack were varied so that there was not an order effect. One group did one first and the other first, so that it was nicely balanced from there. So this is the end of the background information in terms of the material right there. What I'd like to do now is provide you a sneak peek at some of the data, as well as some of the initial translation. So over the next 20-25 minutes here, we're going to get into some of the data. You're going to see a fair number of charts, a fair number of tables that have some of this information, but hopefully the explanation we can provide will help put that in a proper context for you. And please provide us as much feedback as you possibly can in terms of the value of this information, as well as how we might be able to make it more valuable for the fire service. So we'll start off looking at the fire dynamics. And these are some pictures of the residential burn structure itself. It was a full-size structure, about 1,200 square foot, where we had firefighting operations conducted on the inside of the structure. The fuel loads were very repeatable. In fact, we had identical fuel loads all the way down to the really sweet chevron pattern bedspreads that we got from the big box stores. Each of the 12 different scenarios were laid out identically, though in some cases mirrored around the center of the structure itself. The instrumentation layout that we see here, and this is typical for those of you who are familiar with the work that's been done up at UL and seen all of the output and online programs that they have, you would see the exact same kind of instrumentation here. throughout the different bedrooms, living rooms, kitchen. They have differential pressure, transducers, gas concentration measurements, thermocouple arrays, heat flux measurements, and a whole bunch of video and IR cameras spread throughout the structure. Basically, all the information that they typically collect in the lab in Northbrook was put into a van, brought down here, and implemented in the field. This is actually also superimposed on the floor plan of the structure. And one thing I'd like to point out really quickly right here. If you look at the floor plan and go down the center line, which is the front door to the kitchen here, this looks as if it's mirrored around that point, and it actually is. So what we do is include a false wall right here where you see this green arrow, and everything in the shaded area is separated from the fire room. And everything in this light gray area looks almost identical to the layout of the many UL research burns that have been conducted up at Northbrook. So what we'll do on one day is have fires in master bedroom 1 and master bedroom 2 with all this instrumentation. For the next day, we'll actually move the false wall from the left side of the structure over to the right side of the structure, and as we're rebuilding bedrooms 1 and 2, all the instrumentation comes over to 5 and 6, and then we burn in those. Everything in the middle of the living room, the dining room, and the kitchen are all the walls are cleaned off, all the materials are replaced, everything is repainted so that we have a fresh surface for each different scenario. We're also very careful to check the timelines and to be careful about when people come and go throughout the structure, and certain benchmarks are registered. So we're not going to have a chance to go through all these, but this is a typical response timeline. From ignition of the structures to when the firefighters are dispatched, initial water into the different rooms, when the firefighters actually make entry into the structure, exit from the structure, the overhaul crew enters the structure and exits the structure, timelines such as getting the victims out, and importantly right here, when the firefighter reaches the hallway. These are some very important benchmarks that we make sure that we can quantify the effectiveness of the firefighters throughout each of these different tactics and approaches that they use. So now we're going to move to some of the data. And this, again, for those of you who have watched a lot of the UL videos, this should look very familiar to you. On the left-hand side, these are the temperatures throughout the structure at the 7-foot point. Okay, on the right-hand side, we have the exact same temperatures at 3 feet. And again, these are spread throughout the structure, as you can see right here. We have various different, back there. So at each of these green triangles here, there are heat flux gauges from the floor all the way up to the ceiling. And you can see the temperatures here at 7 foot, very near the ceiling, to the 3-foot height, which is what we are interested in for someone who might be crawling, whether it's occupant crawling out of the structure, or a firefighter crawling, or duck walking into the structure. And if you look at the left, we'll start off focusing on the 7-foot temperatures right here. The purple is in one of the fire bedroom 6, and the light blue is in fire bedroom 5. The dark blue here is the hallway, immediately adjacent to those bedrooms. And you can see the temperatures go up quite rapidly, and once they exceed about 1100 degrees, both at near the ceiling at 7 foot as well as at 3 foot, the room is flashed over. So when the firefighters respond, both of these rooms have typically flashed over. You see very high temperatures in the hallway, which is this dark blue right here, and then throughout the structure with the living room, the dining room, the kitchen. What's also interesting to note right here is these two what look like flat lines down here. Those are bedrooms 3 and 4 in here. These bedrooms, very importantly, you see the doors closed. These are just separated from this hallway. These two doors open, 2 bedrooms have flashed over, this small hallway and a hollow core door, about a $40, $50 hollow core door that you can get from any of the big box hardware stores, is all that separates these rooms. And you can see throughout this event that was able to separate that room and maintain control of the thermal conditions in that bedroom. You can see the various different timelines here: ignition, fire department dispatch, when the door opens, and what's really important here is when the nozzle hits the hallway. That's a benchmark that we're going to look at in more detail. I also want to show you what these data look like for the transitional attack. Now you see you get the exact same benchmarks on the top. The one difference here is when the water is first put into bedroom window 2, bedroom 1, then they open and transition into the structure. And again, prior to any sort of firefighting operation, these temperatures are well in excess of 1100 degrees Fahrenheit. And we see that throughout both of those rooms have flashed over. Very high temperatures, again in that hallway, with slightly reduced temperatures, but still high, up into 300-400 degrees, into the living rooms and the dining room for all of those trapped occupants. So really quickly here, I want to compare the 3-foot temperatures. So this is a temperature at 3 foot, say where an occupant might be crawling, where a firefighter might be crawling in, for the structure doing from an interior attack and that from a transitional attack. So this was the exact same firefighting crew. One time they came in and did interior attack, one time they did the transitional attack. And what we can see is very different behaviors in terms of how the water reacts with a fire. So first of all, for the interior attack, we see when the front door is open and they start applying water, as you might expect, all the temperatures go down as soon as the water hits the fire room, but also in the living room, in the dining room, in the kitchen, the bedroom. The firefighters are moving into the structure, putting water on the fire, and again, as we would expect, the temperatures all go down right there. But now let's look at the transitional attack. And one of the concerns that are often stated is what would happen when firefighters are putting water in from the outside. And you can see here, as soon as water is applied in bedroom 2, those temperatures drop down, and we see an immediate response in that hallway. Firefighters transition over to bedroom 1, and again, that water suppresses the fire, and they drop down. And these temperatures in these other rooms, where there would be concern about displacing hot gases from one room to the next at the 3-foot height, we see no increase. In fact, the temperatures begin to decrease. These target rooms look very similar to the temperatures we see for the interior attack. The fire responded to the water being applied to it and did not end up pushing the fire from one location to the other. There's one interesting thing that we can gather from this. I'm going to go back here to the interior attack. If you look at this, again, as I mentioned, we had firefighters doing the operations here. As a result of having them prompted on when to put water on and take water off, the firefighters were doing those operations. And we can see here from this interior operation, here's a case where the firefighters put water on the fire and then transitioned to the other room and put water on the fire, but it didn't completely suppress, and the fire began to regrow in the one room. Started to increase temperatures even down at 3-foot level. While it didn't flash back over, those temperatures increased, and the firefighters noticed it went back and put those fires back down. So now we can measure the impact of different firefighting operations and what happens now when things don't go exactly perfect, both on the interior attack as well as on the transitional attack. Also, very importantly, we looked at the heat flux measured in the hallway just outside those rooms. And again, as soon as we put water on from the interior attack, well, these heat fluxes are on the order of 20 kilowatts per meter squared. These are very high heat fluxes at the 5 foot of the standing level. That would be considered a NIST Class 4, very high heat flux value. Heat fluxes on the order of about 5 to 6 kilowatts per meter squared as the front door is open, and even down on the floor, very low on the floor, 2 to 3 kilowatts per meter squared. As soon as water is applied to the fire, we see those heat fluxes go down. Same thing when we have water applied from the outside in. Once the water is applied, those heat fluxes go down. And what's important is some of the heat fluxes in that hallway. When the nozzle reaches a firefighter, if the firefighter was standing, they would still be getting 13 kilowatts per meter squared, or crawling about 4 kilowatts per meter squared. Yet when we transition in from the outside, by the time the nozzle operator makes it in there, those heat fluxes are down to about 1 kilowatt per meter squared. So a significant reduction, not only for firefighters moving in, but for any occupant that might be coming back out of that structure. So if we want to compare the tactics, how does that affect the temperatures when the firefighter has reached the hallway? We can look at it here both at the 5 foot level and at the 3 foot level. So we'll start over on the right hand side here. In bedroom 1 or 6, these are the bedrooms where there is fire in those rooms. And we see that by a transitional attack, there's still a significant heat load in those rooms, both at the 5 foot and at the 3 foot level, but it's significantly reduced by putting the water in from the outside. Most importantly, in the hallway. During the interior attack, when the firefighters make that hallway, if they're standing there about 950 degrees Fahrenheit and crawling about 600 degrees Fahrenheit, significantly reduced thermal exposure to our firefighters for the transitional attack by the time they make that hallway, as well as with the heat flux that goes from 19 to 5 or from 8 down to 3. We also see that same thing in the living room, the dining room, and all of those other rooms that aren't behind closed doors, where we see an improvement in the thermal conditions as the firefighters are moving in and as we attempt to move the occupants out of that structure. Now, this is a very important piece of information, but it's only one piece of the puzzle. These are the temperatures that our fixed within the location of that measurement location within the building. We know that firefighters aren't fixed in that location. So what we added to this scenario was a firefighter carried environmental temperature. This was mounted to the helmet of the firefighter themselves, so we can see what happens, what temperatures were they exposed to as they moved throughout the structure. And these are just two examples. On the left-hand side, this is for the attack firefighter, and this is for a search firefighter. And we see while they're working on the outside before dispatch, as they're moving to the structure, temperatures are relatively low, and as soon as they move into the inside, temperatures begin to increase quite rapidly. We see a much higher, much more rapid increase for the attack firefighter compared to the search and rescue firefighters, likely due to their relative proximity to the fire, much closer to the fire than the search firefighters. And now this is some of that data. You could find those plots in our interim report, which I'll give you the link to at the end, but the summary statistics here we think are really important. If we look at the effect of tactics from the interior of the transitional attack, for the inside attack firefighters, these are the firefighters who are on the nozzle, the average peak temperature that firefighter was exposed to was about 300 degrees Fahrenheit, 380 degrees Fahrenheit when using the interior attack. That was reduced to about 200 degrees Fahrenheit when the transitional attack scenario. Average temperatures were also significantly reduced from 136 to 108 degrees. Now there is also some reduction in temperatures for the search firefighters, but they weren't nearly as significant as for the inside attack firefighters. But tactic has a significant impact on the environment at which our interior firefighters are operating. And this is something that's not particularly surprising. It's the first time we've been able to quantify that. Now for completeness, I also want to bring in some of this data from the other operations, because this is going to be very important when we transition to looking at how the firefighter responds themselves. So those working on the inside, the average temperatures throughout their response were about 120 to 100 degrees. During overhaul operations, average temperatures were closer to 80 degrees, and those operating on the outside, both the command as well as the outside vent, was closer to 70 degrees Fahrenheit. This took place in the morning of June in Illinois. Okay, so these are the conditions with which the firefighters were operating. So we understand that the environment can be affected by the different tactic that we use, and we also understand that based on where we're operating, we can have very different thermal conditions. What next we want to see is how does that translate to the heat stress that the firefighters face while they're on the fireground. So we know the environment and we know the PPE temperatures. The next step that we're going to look at is the skin and the core temperatures. So this type of data is something you might have seen in the past from work that IFSI has conducted. We will take patches such as this and apply them to different skin portions of the body. In this case, what we applied to the upper arm, and we were interested there on what was the skin temperature underneath the bunker gear. We also applied one to the back of the neck, so we could measure the temperature of the skin underneath a knit hood. Both of these communicated with a wireless transmission system that firefighters carried in their coat pockets, so that we could track and characterize these temperatures throughout. So for time, I'm going to skip ahead and just show you some of the data from the skin temperature. And I want to start this off by saying this is the average peak skin temperature for each of these different groups, for the outside command, for the outside vent, the inside crew, and the overhaul crew, averaged over all those on the interior operations and for the transitional operations. And what you can see is, first of all, there's a significant elevation. These firefighters started off, their skin temperature typically was between 90 to 92 degrees. Even for the outside command pump, that temperature increased to about 97 degrees, and for all others operating on the fireground, increased to between 99 and 100 degrees. Now, while there's some variation in here, these aren't significantly different, which might take you back for a second, because if you think about it, those working on the firefighter reached peak temperatures in some cases of over 400 degrees Fahrenheit, yet those on the outside vent, those temperatures were typically below 80 degrees. However, they were all wearing bunker gear and working, in these cases, at some point based on heart rate near maximal exertion. So we see these skin temperatures increase by about 8 to 9 degrees Fahrenheit, which is important in and of itself. We also want to look at the temperatures on the neck. And you can see here very similar types of data here. A much more significant response for those who are doing heavy, strenuous firefighting operations, the outside vent and the inside and the overhaul, much larger than we have for the outside commander pump. But what I also want you to take a look at really quickly here, while we didn't see any overall effect of the tactic, this is one scenario where there was an interesting outcome from the tactic. If we look just at those who are operating on the inside of the structure, we see about a 1 degree Fahrenheit lower temperature on the neck for the firefighters conducting transitional attack as opposed to those on the interior firefighting operations. Now this difference is small, and the physiological impact is still being understood. But it is important to notice this difference. It can affect the ability to dissipate heat from the core. It can also alter the absorptivity of the skin, which could be important for risk from thermal exposures, particularly because of the work that we've done in the past with our friends at NIOSH that have shown the neck to be some of the area that has some of the highest exposures on the fire ground. So the physiological impact of this is still being understood. In each case, the temperatures are well below anything we're concerned about risk for burns, which is critical and what we would expect for this type of scenario. But when we look at how it affects the body, we want to see how that translates into the core temperature. And this is the last bit of data we're going to share with you today before we open this up for questions. And what this plot shows here is typical core temperature responses during these firefighting operations. Now we can measure this for all 12 firefighters operating at all 12 different events, but just showed 4 different types of operations. And the gold here is the inside search operations. Green right here is the outside pump operator. The brown, outside vent, and black is the overhaul operations. In the beginning, core temperatures start out 98.5 to 99 for the most part. We see the initial rise in temperature begins for the inside search because they started doing strenuous operations right away. We do see an important rise in temperature for the outside pump operators as well as incident command. They were wearing bunker gear, and even though they weren't doing heavy physical strenuous labor, they were moving around in a fully encapsulated situation. We also see very rapid increases in the core temperature of the outside vent, as you can see right here. It's delayed a little bit, but once they begin throwing ladders and chopping holes, we see very significant increases in core temperature, even though they're operating on the outside of the structure. And then same thing here for the overhaul. The initial operations are relatively low-key, relatively small increases. They're setting up RIT or pulling a second line, but once they transition to the inside, when the search and attack comes out, we see very rapid increases because we all know, those of us who've done overhaul, it's heavy physical work to be pulling ceiling, to be moving things around, to be mucking out the scene. So this data is the first time we've been able to compare each of these different conditions, particularly in something that is as realistic a scenario as we have on the fire ground. So I want to show you just some summary data from each of these. And this can be somewhat surprising. It certainly was for us. And first of all, I'll tell you one of the conclusions out of this is that we're seeing no difference overall or for any of these positions for the interior attack or the transitional attack. The maximum core temperature that we measure is 101.0 for interior, 100.9 for transitional attack, and very small, non-significant differences for each of those different positions. Even if we look here at the inside where we had slight differences for skin temperature, it did not translate to differences in temperature or core temperature. What was somewhat surprising to us is repeatedly we found the highest core temperatures measured for the outside vent and the overhaul scenarios, in many cases 102 degrees and beyond. And again, this is the first time we've been able to measure those in an actual realistic scenario. Another way that we can look at this data is the core temperature change, and I want to show this for one very important reason. This is the change in core temperature from the time firefighters were dispatched to the maximum temperature that they experienced. And I want to put this in the context of someone working through multiple cylinders of air or having multiple different activities that they have to conduct. If there's not enough manpower on scene, like we had where we could have one group doing the interior operations and the next group coming in and doing overhaul. All of these temperatures began with a firefighter in relatively rested state. So we saw overhaul operations getting up to 102 degrees without any significant effort ahead of time. Now instead, if the firefighters who just completed the inside operations had to get a new cylinder of air and come back and do overhaul, say instead of starting at 98.5 or 99 degrees Fahrenheit, now they started at 100 degrees Fahrenheit, but conducted overhaul and went further 3 degrees higher than that, we can see now those core temperatures, instead of being 102, might be at 103 or beyond. Or what's even more concerning might be a firefighter who's gone through and conducted the outside vent. And they may or may not have gone on air, so the incident commander can say, all right, you've not used any air, we'll send you right in and do overhaul. And so now, after they are beginning, instead of at 99 degrees, at possibly 101.5, and their core temperature may go up another 2 to 3 degrees as a result of that. Now we're getting into core temperatures where we may be significantly concerned about the physiological implications of these. So this information is available, and we're presenting it in ways, hopefully, that you can take back to your operational reality. You may not have manpower coming in to do these operations independently, but this is the type of thermal stress and thermal strain that we see as a result of these operations. So what I'd like to do now is wrap up with just a few interim recommendations and show you where you can get some additional information. And again, the goal is to translate this research into some tactical operations or some considerations for you. And what we've found, again, is the importance of applying water as rapidly as possible. We found that the thermal conditions improved throughout the structure after water being applied. We didn't find any case where water was applied from the inside or the outside that the other rooms had a significant jump in the temperatures. It's also critical to complete the search as rapidly as possible, because some of the fire-drying gases may remain elevated post-suppression. We need to be able to ventilate and get those individuals out as rapidly as possible. We need to train on coordinated attack for a successful response. I didn't show one specific scenario, but a transitional attack scenario, I'll discuss it briefly here, where the firefighters put water in from the outside. Then as they transitioned in, there was a delay in getting into the inside due to a forcible entry issue. The fire regrew, and in fact, in one of those rooms splashed back over by the time the firefighters transitioned back in. That was not as well coordinated as we might like to see this type of response. So we saw, because we introduced the variability of the actual firefighters, a significant variation in terms of the time it takes to get victims out, as well as the difference in the thermal conditions based on how much water is being applied and how rapidly the conditions change as a result of the coordination on the fire ground. One of the important things we see here is the importance of a closed door to the public as well as to the firefighters. While we saw 2 rooms fully flashed over, a bedroom right down the hallway from that with a hollow core door closed, those temperatures remained very low and the gas concentrations all remained very low. Now it's important to remember that that door is not rated for a long period of time, so it's not a rated assembly at all. And in each case, the door took a significant amount of damage. The importance of transitioning to the inside, or the importance of getting in and searching for these victims, cannot be reinforced enough. Because while we see a significant amount of protection from that door, that protection can be limited. So we have to make sure we get in there as rapidly as possible to help find those victims, survivor victims, behind the closed door. This is also the first time we've been able to connect some of the fireground thermal data with the firefighter thermal data that we have here. In order to reduce the thermal and cardiovascular risks, the first thing we need to realize is that thermal exposures on the outside vent and overhaul operations can be significant, even if the ambient temperatures are small, and we might not expect there to be a high risk as a result of those thermal conditions. Wearing the fully encapsulating bunker gear does a great job of protecting us from the thermal conditions that we measured in this study, but it also does not allow the body to breathe or the temperature, core temperature, to be dissipated as efficiently as it would without the full encapsulation. We did see some effect of tactics on the skin temperature of the neck, but it was not a very large effect. There was some small effect there, but there was no effect that translated into an impact on the core temperature. But as we translate this into understanding the cardiovascular impacts on the fireground, we have to realize that the different roles on the fireground, we have to understand that there is a significant physiological strain and potentially a thermal strain regardless of what those positions are. It's important that firefighters receive a 1582 physical by a knowledgeable physician each year. The importance of physical fitness cannot be stressed enough, because we might assume that working on the outside, that outside vent, is a low stress scenario. We might not initially view that as the same risk of operating on the inside of the structure, but we see that the thermal stress on the body is still quite high. So we need to consider incident scene rehab for the work that is being done, not just the number of bottles of air that a firefighter has gone through or the amount of time that they've worked on the fire ground. So this information, you can find our interim report some of this background information, if you go to the website, the fsi.illinois.edu/research, you can find the interim report that has some of this background information, some of the initial data. You can also follow us on Twitter at IFSI Research, where as new information comes out, such as the paper that's being currently peer-reviewed by our scientific peers, is going to be made available as rapidly as possible. This is also where we're going to announce the toolkit and any other outcomes from this study that will be made available to the firefighters, both on our website, on UL's website, and on social media from this point forward. So that's going to bring us to the end of my presentation here. What I would like to do now is open this up for questions, and I believe I'll at this point turn it back over to Ari for moderating that.
Thank you, Dr. Horn. I appreciate it. We'd like to start answering questions now from the audience at this point. So please type your questions into the chat box at the bottom left corner if you have one. We've already received several from the audience. The first one is, with the increase in core temperature, how does that affect mental status, cardiovascular effect, dehydration, and muscle fatigue? And there's a related one. Is stress or mental stress a significant factor in raising skin and core temperatures, exacerbating those resulting from physical work and ambient temps?
Okay, this is an excellent question, and something that a history of research has been done at the Illinois Fire Service Institute, Denise Smith and Steve Petrozello. And again, if we go back to this website right here, if you go to that site, you can download a series of fire service reports and also find a great deal of research has been done to focus on the physiological and psychological stress and the impacts between the two. And there is a convincing body of evidence that suggests that increases in temperature, increase in stress can impact decision-making capabilities, as well as the psychological stress impacting the response, the fight or flight response. That has an impact both in the thermal response as well as in some of the decision-making aspects. It wasn't a specific part of the study that we conducted here, but we feel we'll be able to link this back to some of those studies that existed looking at that aspect. The other part of the question, I believe, focused on the cardiovascular implications. And that is a component that we're currently working on and writing up right now. And yes, the thermal strain has a significant impact on the cardiovascular responses. The way the blood, we often think about the cardiovascular system as a pump, a pipe, and a fluid, just like any other fluid dynamics problem. But the fluid, the blood, actually responds to different types of stressors differently. It responds to heat. It responds to the fight or flight response. It responds to heavy muscular work, and the chemistry changes quite significantly. And we're working through right now understanding some of those implications and tying those back to the thermal stresses that we see here. So that information will be coming out here within the next few months, and we'll hope to distribute that at webinars such as this or the various different ways that we distribute information at conferences around the country.
Thank you, Gavin. I have another question for you. What are your findings? What do you see for a best practice for Fireground operations? And should drivers look at not wearing their set of reduced risk?
So looking at best practices on the Fireground and not wearing turnout gears to reduce the risk. Are those the questions?
Yes.
Okay. Well, the best practices that we're looking at right now, we're still accumulating all of this information. There's a lot of different things. The goal from here in terms of best practices is to provide the information out to the fire service so that they can determine what the best practices are. The best practices for a department that has 6 firefighters on each apparatus might be very different from a small rural department that might only have 2 or 3 firefighters on each apparatus. Someone who can bring 50, 60 firefighters to the scene will have different things to consider than a department that might only have 10 firefighters operating on the scene. So we are providing, what we're hoping to provide here is the data that can allow the departments to make these decisions on their own. There are certainly significant impacts from the different tactics that might be applied, but there's also very important things that you need to consider based on the fireground operations that you have. We didn't have a fence and firefighter eating dogs involved in this scenario. That could change how rapidly we can get to a certain structure. There might also be a much longer delay in the forcible entry process that might delay how rapidly we could get inside the structure. Different floors of the structure can significantly impact how rapidly one tactic can be employed versus the other. We also need to put this in the context, and I want to be careful for everyone that this is one aspect of this study. We're going to have a lot of different view when we look at the chemical exposure. We need to be able to balance those in each department or each individual. We want to get this information out so you can balance those risks and make those decisions on your own based on the science and the tactics that we're seeing here. In terms of operations without bunker gear, these are very important things that we have to balance. If you're working on the outside of the structure, wearing the bunker gear will certainly reduce the ability to dissipate heat. But the bunker gear also provides a level of protection from the fireground gases and particulate. Depending on where you're operating that pump, we could see a significant exposure if the gas or the smoke doesn't lift very heavily. So that's an important thing that has to be balanced, again, based on the operational reality. If it's 110 degrees on the outside, you might choose to reduce the thermal risk and take a higher risk from an exposure perspective, or vice versa. Or you might look at different things you can use to provide that protection from the fireground exposures that might not have as significant of a thermal burden. So the goal is to provide information to the fire service, but those decisions still need to be made locally.
Thank you, Dr. Horn. I think we have time for one more. Data here on conditions. Firefighter. Or victims trapped inside.
Okay, sorry, cutting out a little bit there, but I think your question was, we're looking at a lot of data for the firefighter, but what about the victims? Is that correct?
Correct. Roger.
And this is actually a really important aspect of this study that we didn't get to cover here. For the first time, we were also able to instrument some victims in this structure. We're able to look at the rescue Randys that were full size. So as firefighters were rescuing them, look at the gases that they were exposed to, look at the temperatures that they were exposed to when we moved them from one area of the structure to the next. And I'd say in many ways, while this is an area that is currently being written up and evaluated right now, what we see here are the differences in the temperatures from the interior to the transitional attack. While we had a significant impact on the ambient temperatures, that didn't really translate to very significant impacts on the firefighter themselves. A small decrease in the neck skin temperature, but no real impact in terms of the thermal strain of the firefighter. And a lot of that is being attributed to the gear that we wear. It does a great job of protecting us from the environment, at least in these conditions. Now for the occupant, that's a whole other story. They don't have the gear that we're wearing. So this change in hallway temperatures from down on crawling level from about 600 down to 150 might be even more significant for the occupant than it is for the firefighter themselves. Also, if we look at this data, again, think about the value and the importance of the closed door. Remember, just outside of this closed door is this hallway. So if a firefighter is operating on the inside of the structure, and maybe they're searching ahead of the line, haven't had a chance to put water on the fire, we might have an occupant that's sitting behind this closed door and realize as soon as we open that door, these are the conditions that have a free pathway to go into that room. So as we're operating on the fireground, controlling the door until we're ready to make a rescue, or possibly even closing that door behind us in order to get the victim out another location if that is a viable option. We need to understand the exposure that we might be putting to firefighter or putting our occupants in that could be protected by those structural components. Now, these are just a few thoughts off the top of my head here, but more data and more information is going to be coming out on that aspect in the not too distant future. And again, a component that we think have some new information about the risk to the occupants as a result of the firefighting operations, as well as the risk to the firefighters themselves.
Gavin, thank you so much. That's all the time we have today. I'd like to thank Gavin for providing us his perspective and sharing these valuable findings with all of us. For all of you attendees, thank you for joining us. Please take a few moments to fill out our questionnaire at the end. We want to hear from you about future topics you would like us to cover. We did receive many questions that we didn't have time for. We will try and get those listed and answered by our presenter and sent to all of you as well. We hope to see you at our future webinars, and we wish you a great afternoon.
Thank you, Ari. Appreciate it.